So in this video we have 6 different chemicals. 1 and 2 are the same chemicals, 3 and 4 are the same chemicals, and 5 and 6 are the same chemicals. The only reason that they are different is because they have different concentrations in them. So now we're moving to the plate that we'll be putting inside the world plate reader. And as you can see, A1 through A6 are the chemicals that we are testing with. But for this demo, we will only be using 2 chemicals.
This is our spectrometer. We've made a couple of adjustments since last time. Now, what we have right now are the same gratings, but the tilt is different because now we are using a different laser, and this time it is 532 nanometers. We felt that the detector that we are using is going to perform better. In fact, the efficiency of the camera is more suited for wavelengths in the visible, as well as 500 plus. So the gratings are the same, but they're tilted at different angles due to the switch of the laser. Now we've also added a 532 nanometer notch filter, which rejects the 532 nanometer wavelength. You can actually see it a little bit right over here. See if I can get a good view. But those are the changes that we have made to our system so far. The probe that sits underneath is also catered for 532 nanometers. So this is our GUI. This is what we'll use to control our device. We're going to go ahead and try to show you some Raman measurements. Julia?
Hello, so this is our well plate reader that we'll be doing our demonstration for you guys today. So as you can see here, it's the 532 nanometer Raman probe that will be analyzing our chemicals today. Currently, it is sitting under the wrong chemicals, so George will move it to cell A1, which is right here, which is potassium chlorate.
Alright, so we have our Raman probe sitting underneath the chemical that we want to measure. So let's go ahead and up the exposure time until we get good visibility on the fringes that forms by the SHS. Right now we're about half a second, so let's maybe go up to 2-3 seconds. Okay, I think that might be good. Alright, I'm going to go ahead and click File, Save Image. I'm going to call this Potassium Perc 4. Go ahead and change that real quick. Save. I'm going to go over to here, click Get Spectrum, go to where I saved the image. And it was Potassium Perc 4. Going to select it. And as you can see here, we have the Raman spectrum of potassium perchlorate. Alright, so we're going to go ahead and do another full run through, full measurement of another chemical. Right now the probe is sitting underneath right here over at cell A1. So let's go ahead and switch chemicals. We'll move over to cell A4 that has ammonium nitrate in it. Okay, so we're right over it. Let's go ahead and put the safety cover on. And we'll go ahead and enable the laser. Alright, laser's definitely on. Alright, now we're setting at about 83 microseconds. So let's just go ahead and increase it. Alright, we're already starting to get some visibility on the fringes. We're at about 100 milliseconds. Let's go up to maybe half a second. Okay, I think I'll just keep going. I think I'll put it at the max. I'll put it at 10 seconds. Might get stronger peaks this way. Alright, so let's just go ahead and wait 10 seconds. Okay. Roughly 10 seconds. Let's save the image. Call this ammonium nitrate. Let's call it 10. Alright, we're going to go ahead and click Get Spectrum. Go to Pictures, where I saved it. It's BMP. And then there's our ammonium nitrate 10. Let's go ahead and save. And let's go take a look. And there you have it. There's the spectrum Go ahead and zoom in on some of the finer details. This is recalibrated, the x-axis, by the way, to fit better lines on the mercury light source that we used. There you have it. Ammonium nitrate, full measurement. So our known peaks when we measure mercury are 546, which corresponds in this case to about 265 pixels, 576 at 731, and 579 nanometers at the 829th pixel. When we have it set up like this, our R squared is about 0.9887, and the resulting linear calibration curve can be seen on the bottom right. I would like to note that peaks that shift by 800 centimeters inverse or lower are for some reason appearing weaker on our SHS. It may not be sensitive enough to pick them up at this stage, so the calibration is not perfect. But that being said, we are able to pick up specific wavelengths within our range, our spectral range, and the calibration that we have seen so far seems to be lining up, and we will show that on the next couple of slides. So looking at the bottom image, we can see that there are about two sets of peaks. You can see two on the left at 400 and roughly 700 inverse centimeters. Again, as previously mentioned, those peaks for some reason are not showing up on our plots. Again, I'd like to note that in our new setup, the 532 nanometer laser is going through our system, though our gratings are blazed at 780. We had to make a switch from infrared to 532 in order to work with the detector that we had and to allocate some space on our system such that we can pick up certain signals within our spectral range that shift. So the Raman shifts that we can pick up is the 1000, or in this case I believe it's 940 inverse centimeters, as well as the 1060 inverse centimeter peak. You can see the doublet on the bottom right of both plots. We have some arrows pointing from peak to peak, so we can pick up the 940 inverse centimeter peak pretty well, and the doublets are appearing pretty well as well. But also, if you take a look at on our plot, which is the top image, you can see at around 543 nanometers, there is a very tiny peak, but it's large enough to be seen. This could be one of the peaks that appear on the bottom plot, but it has an intensity, a very slight intensity of about 8.8. So now we're going to go ahead and compare the intensity levels based off of two different concentrations. The concentrations that we had prepared were a 1750 milligrams per milliliter sample, as well as 550. For both of these images, the exposure time is set to 10 seconds, and for convenience, the scale of the images are set with a maximum count level of 160. Now, if you look at the top image on the left, you can see the fringes. Comparing the fringes on the top and the bottom, it is clear that the top fringes are brighter than the ones on the bottom. And you can notice for the same exposure time and different concentration levels that a 550 milligram per milliliter concentration does in fact bring back less of a signal. The intensity is less compared to the larger concentration sample.
This slide will be focusing on sodium sulfate. So as you can see on the spectrum Raman shift versus intensity, we use that graph also by another group that did an SHS measurement on sodium sulfate. We use the orange line to reference what we got in our well plate reader when we measured sodium sulfate. So as you can see on the left, it has two distinct peaks, one around 1,000 and one around like 1,100, which is a doublet peak. So since our SHS is around 532 nanometers, Our Raman shift will be looking at 1,000 and up because that's our range. 1,000 and down wouldn't really help us in our case. So as you can see, in our SHS sodium sulfate measurement on the right, we have that distinct peak in wavelengths, not Raman shift. And then we have those two doublets which correspond with the sodium sulfate on the left. So with this slide, it shows two different comparisons of sodium sulfate, but one has a larger concentration, one has a smaller concentration. And they both have an exposure time of 10 seconds. So as you can see on the larger exposure time, the fringes are brighter, they are more distinct, and with the corresponding spectra, the counts are higher, and you can more visibly see the doublet that we talked about in the last slide. Compared to the smaller concentration, the fringes are not as distinct as the larger concentration, and also with the spectrum that is associated with it, it has a lower count, and some of the lines that we should see that are distinctive to sodium sulfate is not distinctive because it is not enough Raman signal to detect those.
So when we measured ammonium nitrate, we were able to observe three peaks that were noteworthy. We can see that comparing the 9 or 1046 inverse centimeter peak, that would correspond to a shift from 532 nanometers to 561 nanometers. So if you look at our middle plot, you can see that the largest peak, which corresponds to the 1046, is sitting at around 562, 563 nanometers. So this, though there is a slight difference, our calibration sees that our peaks line up at roughly the correct location. Now, if you look at the right side, sitting at around 590 nanometers, we believe that this might correspond to the 1500, 1600 inverse centimeter peak as seen in the reference spectrum on the right. The intensity of this peak, we're not entirely sure why this one is larger per se than the doublet sitting in the middle, but it should be noted again that these gratings were tilted in order to recalibrate our system. So this might be partially why the intensity of these peak is larger. But for the most part, we believe that we at least have the positions of the wavelengths properly set. Now, comparing the intensity levels for different concentrations with ammonium nitrate, again, the exposure time is kept the same, and we have two separate concentration levels. All of them were prepared each with 1750 and 550 for each chemical. Now, it's not as immediately obvious as before in terms of at least the brightness of the fringes themselves. If you look at the top left image, the fringes, that's the 1750 milligram per milliliter fringes for ammonium nitrate, and compared to the bottom, they actually look, just based off of observation, they look pretty much the same. But when you look at the plot of the spectrum on the bottom right, you can see that there is a noticeable difference in intensity levels compared to the top spectrum. So though we have different concentration levels and the fringes look roughly the same in terms of intensity, we are seeing somewhat of an intensity drop from concentration level to the next.
So to make sure that our spectrometer was accurate, we used 10 measurements for potassium perchlorate. And so for this one, we use concentration level 2, which has the lower concentration of the two that we used. So as you can see on the left, we have a table, exposure time versus intensity of a 562 nanometer peak. And you can see the numbers that are associated with it. And the average intensity is 106.912. And on the right, it has the graph that is associated with the table, just to give another visualization. So as you can see, around 1 millisecond, the laser in our spectrometer starts to saturate. And as you can see, we also put error bars to show another visualization of how accurate each distinct peak is. So since the error bars are kind of large, that means the points are more spread out and not as concrete as smaller ones. So to make sure that our spectrometer is accurate, we use 10 measurements for potassium chloride below level 1 concentration, and that is the higher concentration of the two. And as you can see, again, on the left side, we see a table of the exposure time versus intensity and a graph that is associated with it. And the average intensity is 111.9529. And on the graph on the right, since it shows large error bars again, that means the points that we used, or is shown below, are more spread out and not as concrete.
So we have two separate plots that illustrate the relationship between intensity versus increasing concentration level. We have two plots, one with an exposure time set to 10 seconds, and the other plot with an exposure time set to 5.2 seconds. Though we only have two concentrations prepared, we feel that these plots are still able to illustrate the relationship that as concentration increases, so does intensity. But of course, it would always be helpful to have more samples of concentrations set up. However, we did notice that for a certain exposure time, the intensity level saturates, and this can be illustrated in the previous slides. But at around 5 to 6.5 seconds, the intensity begins to saturate, and as you increase your exposure time, the intensity tends to drop and stabilize at a certain level. But overall, we can see through these plots that as the concentration level increases, we can see that the intensity increases as well. So jumping from 550 to 1750, we can see that the intensity increases.
Oh, hi. So today we're going to be demonstrating our safety interlock. As you can see right now, it's unlocked. And with the GUI right there, made by my friend Sebastian, we can be able to unlock it and lock it at will. Right now it is in the lock position, so it is very difficult to open with about 3,000 newtons of force required. And as he unlocks it now, we can see that it is now unlocked. We put it like this for a better vision. The final design, we'll have it like this. And as you can see, our interlock is built in, and it is open now. And
what's the point of our interlock?
It's to keep people outside, because as you can see, there are dangerous lasers in here, and it's a safety measure.
As you can tell, the lasers come right out, so for that reason, we have this to prevent anything like that from happening. I'm actually gonna unlock it again, and you cannot pull that out.
Yeah.
Hi, this is Juan Restrepo. Here I'm demonstrating the PCB as a whole. We have the power supply unit coming in through here. On this side we have the fan, which is working right now. This fan can be turned on and off based on the GUI from the PC. This is going to the USB into a microcontroller. Here we have this humidity and temperature sensor. This humidity temperature sensor connects through UART through this USB cable and to the PC here. We see that we have a 13 Celsius and 10% RH. Every time that we pull the sensor, we get new values. Sometimes we're getting a surge of current, which gives us very high values at times, but they go right back down. And the reason we see such a low for the Celsius right now is because we have the fan right now running onto the sensor.
The next software feature to show is the laser. So at the moment, it is turned off. As you can tell, when I do this, this is where the emission comes out. There's no laser here. But when I go to edit laser, and I hit this button, the laser should come up, the controller should come up. There it is. I'm going to change this port to COM5, the baud rate to 9600. This corresponds to the laser itself. I'm going to hit add device, and here you can see a sort of interface for the laser. First thing I'm going to do is enable the laser. So as you can see here, there's light turned on, laser enabled. And however, there's no output because I haven't given it any output voltage. So I'm going to increase this to halfway, which is 0.6 volts. And you can clearly see that the amps went up and there's a laser coming out of this. And when I crank this up to the max, it'll be much brighter, as you can tell. These are some more of the software features for our project. This is the GUI. It will be controlling most of the features or most of the hardware in our project. First thing we're going to do is initialize the motor. I know that the motor is on column 4. We'll go here. We'll go to column port 4. This is just device manager. You're going to initialize the system. Okay. And you can see it moving a little bit. For the motor, it's controlled by this area. So what I'm going to do is actually change this to 100,000 microsteps because that's the equivalent of one whole well. That's 1, 2 wells, 3 wells, so on and so forth. And when I want to go back to the original well, I hit go to start, and there we go. Another thing that we have is this capture image button. So what this will do will, we don't have anything in the well plate, so this doesn't really work, but when we hit capture image, the laser, or the camera captures the image from the laser and stores this image. It'll show up as a figure, and you save this image to wherever you'd like. And then once you've done that, you can hit get spectrum. I have this old image that doesn't really have anything in it, but it's a spectrum, and so I had it saved. I'm going to run this, and you should be able to see here that this waveform appeared that corresponds to that image. So whenever you hit the spectrum, hit get spectrum, you choose the image, the calculations occur, and Fourier transform and everything, and you end up with this graph in the interface. That's what the old white box used to be.